Have you ever wondered which type of kart is the most aerodynamic? Recently, a friend asked me to simulate an oval kart to see just how aerodynamic it really is. But what exactly is an oval kart? As you may know, there are several types of karts: sport cars, rental cars, enduro cars, and then there are oval karts. These are a unique type of racing kart designed for circular tracks, much like NASCAR, and are especially popular in USA and Australia. They race both on dirt and asphalt, and their design is quite different from the typical sport kart. Oval karts feature smoother bumpers, a more upright and simpler front panel, larger side pods, and notably no open wheels. Everything is enclosed and with minimal gaps between body elements. Logically, this design should offer a big aerodynamic advantage, but does it really do? Today, we'll simulate it in the digital wind tunnel and find out how aerodynamic it really is. At first sight, we can see a very high pressure zone forming at the front of the kart, especially around the large front bumper. This is expected, but thanks to its smooth rounded shape, the high pressure is reduced along the sides compared to the typical sport kart. Looking from the front, the highest pressure areas appear around the bumper, the knees, the front panel, the engine top and the helmet. Now let's stop at the front panel. This is one of the most unique features of the oval kart. It's quite upright and flat, which redirects much of the airflow upward. This helps reduce the pressure around the driver's chest and helmet area, which is a good thing. However, not all air is deflected. Some still enter the cockpit through the gap between bumper and the front panel. I believe that if the front panel were longer or extended lower, it could reduce cockpit airflow even further. Also, the current front panel is very basic. In sport cars, we see a wide variety of front panel designs that shape airflow differently. For instance, the Birel S18 panel directs airflow upward, but also carefully limits the amount flowing over the helmet, reducing the low pressure zone that can form near the helmet region. A similar concept could benefit the oval kart. Moving to the center section, another major advantage is the lower driver position. In oval karting, the driver sits significantly lower than in sport karts, which is excellent for dynamics, since the driver is one of the biggest sources of drag. Lowering their height means less surface area for the air to hit. One important detail in this 3D model is that the engine is enclosed within the bodywork. We can clearly see in the pressure map that very little airflow reaches the engine area. While this is great for drag reduction, it could lead to cooling problems and reduce engine performance. Definitely something to keep in mind. Let's now talk about the wheels. Any aerodynamist will tell you that wheels are a nightmare for clean airflow. They ambush the airstream and create turbulence, drag and all kinds of flow separation. That's why in motorsport, engineers are constantly trying to isolate or shield the wheels. In Formula 1, wheels are open, but there is a whole range of aerodynamic elements up front designed to control the airflow around them. On the other hand, lemon cars enclose the wheels entirely for better performance. Oval karts follow a similar approach. The wheels are isolated from direct airflow. In the wall shear stress graph, we see higher friction around the front wheel area. That is actually a good sign. It means more downforce on the front tires, which improves grip. Unfortunately, the same can be said for the rear wheels, where we notice flow separation, a sign that airflow is detaching. I believe that adding small spoilers at the end of side pods could help energize the airflow and increase rear downforce. There is one more detail I really like: the use of end plates on the aero elements, especially the side pods. In aerodynamics, when air flows over a wing, high pressure buildups on top and low pressure underneath. This difference can cause airflow to swirl and create vortices, which reduce efficiency. That's why engineers add end plates, 3 wings, to contain and clean up the flow. Here, the side pod end plates help keep the airflow structured, pushing it forward instead of letting it spill into the cockpit. A simple but very effective design. Oval karts don't just race differently, they are built differently with aerodynamics and the core of their design. from the lower driver's sitting position. The fully enclosed bodywork, the smooth front panel and the side pods, with helpful end plates, it all contributes to a much lower drag coefficient. In fact, the oval kart we tested achieved a drag coefficient of just 0.47, compared to other karts with the same engine setup but less optimized bodywork. That's a significant improvement. Of course, there's still room to improve, like reducing airflow into the cockpit or improving rear downforce, but overall, I really like the oval kart, and I can confidently say this is the most aerodynamic kart I have ever tested so far.